Okay, Assalamualaikum and salam sejahtera. So let's summarize chapter 10. Okay, what we have discussed before in chapter 9, we are discussing about the simple harmonic motion. Okay, so let me differentiate first. What do we have in chapter 9 and chapter 10? Okay, in chapter 9, we are discussing about the simple harmonic motion where the main equation is y equals to a sine omega t. So we are discussing about the oscillation of particles, isn't it? So the graph given is y against t. According to this main equation, we are discussing about one particle only, which is oscillating upwards and downward here. And as we know, under simple harmonic motion, the object is moving from one amplitude to another amplitude through the equilibrium, repeated again and again, which is under periodic motion. So the graph given just be like this. Alright, so we are discussing about one particle at different time. What happened to the displacement of the particle at t1, t2, t3 until tn? So this is the displacement of one particle at different time. Okay, that one is under simple harmonic motion. But in chapter 10, we are discussing about wave. Alright, the main equation is y equal to a sine omega t plus minus kx. So in this equation, we have two different things. The first one is the simple harmonic motion, okay, of the particle, and the second one is the wave propagation, okay, which is kx here. All right. So what do I mean? Okay, let's say initially this is the wave. So the particle just look. This is the first particle, and this is the second particle. After a few seconds, the wave just propagate to the right. So at the same time, the particle oscillating downwards already. The first particle oscillating downwards, while the second particle just oscillating upwards. Alright. So this is the displacement of the first particle and the second particle. At the same time, the wave also propagate to the right by x. So we have two different things, which is the propagation of particle, and which is a sine omega t. At the same time, the propagation of wave, which is plus minus kx. So the graph given now is y against x, okay, representing, okay, there are so many particles which is oscillating upwards and downwards. At the same time, the wave just propagate. It can be to the left or to the right, okay. So according to the main equation here, y equals to a sine omega t plus kx, or y equals to a sine omega t minus kx. So plus and minus, what does it mean? Okay, by having plus kx means that the wave just propagate to the left, while by having negative kx means that the wave just propagate to the right. Okay, so this is the way how do we know the wave propagation. Okay, the direction of the wave propagation is it to the left or to the right, based on kx. Alright, at the same time, what is k? K is the wave number, where the equation is 2 pi over lambda. Alright, the wave number also, we know it as number of wave in a unit distance, where the unit is per meter. Okay, for other symbol, it's still the same with chapter 9 before, which is y is the displacement of the particle, a is the amplitude, alright, omega is the angular frequency or angular speed, alright, t is the time, and x is the wave distance, yeah, the displacement of the wave. Okay, so in this chapter we have two different v or speed. Okay, the first one is v equals to f lambda. This is the speed of wave. The second one is vy. Vy equals to dy over dt. So we need to differentiate y with respect to t. Okay, for this we are discussing about the speed of particle which is under oscillation. Okay, as we know, vy equals to a omega cos omega t plus minus kx. Again, under differentiation, for the first differentiation, which is y with respect to t, you will get this equation. So this is the speed of particle which is under oscillation. So remember, v and vy, they are different. Okay, the speed of the wave and speed of the particle. Basically this is the main equation of the wave. Alright, for the first differentiation, you will get vy, that one is the speed of the particle. And for the second differentiation, which is dv over dt or dy squared over dt squared, giving you negative a omega squared sine omega t plus minus kx. So this is the acceleration of the particle which is oscillating, okay, upward or downwards. Alright, so remember Vy and Ay just for particles only. And in this chapter we have two different graphs, which is y against x and y against t. So what is the difference between these two graphs? Okay, for y against x, we are discussing about the all particles at instant or at particular time. Okay, what does it mean? The graph now showing you the displacement of all particles, okay, at certain time or at particular time. Let's say at t equals to 1 second, and this is the position of the first particle or displacement of the first particle, the displacement of the second particle, the third particle, the fourth particle, the fifth one, until the nth one. Okay, so we are focusing at certain or particular time for all particles. Okay, and from the x-axis we may know lambda, one complete oscillation here presenting lambda lah. Okay, alright, the distance between crest and crest or trough and trough representing lambda, and then the distance between crest and trough representing half lambda. Okay, alright, and then for y against t graph, okay, we are discussing about the position of one particle at different time. Okay, what does it mean? Let's say we just focus on the first particle here. Okay, at t0, what happened to this particle? At 2 seconds, what is the position of the particle? At the 3rd second, the 4th second, the 5th second, okay, what happened to the particle? So the particle just oscillating upward and downwards, isn't it? So this graph now representing the displacement of that particle at different time. What happened at t0, at t1, at t2, at t3, at t4? Okay, we are focusing on one particle only, okay, which is at different time. And here from the x-axis, which is t, we may know the period lah, and where the crest, the distance between crest and crest representing period, or between trough and trough representing period. Okay, alright, and then let's discuss about the standing wave. Okay, before this we are discussing about the progressive wave, alright, where the wave just propagating, it can be to the left or to the right. Okay, so we are discussing about the energy transfer lah by the wave. Now let's discuss about the standing wave. How do we get the standing wave? There must be two equal wave which is propagate in opposite direction. And for example, by having the first wave now, also the second wave, and then these two waves just propagate in opposite direction. So what happened? They will overlap to each other, or we are discussing about the superposition. So the superposition between these two waves giving you or producing you a standing wave. And it seems like there is a wave, but it doesn't propagate. That is why we call it a standing wave. It seems like the wave just keeps static there. Alright, okay, so according to the situation, by having two different waves now, which is y1 and y2, this is y2, okay, so they just superpose or overlap to each other, producing the standing wave. So the symbol is capital Y here. Capital Y now representing the standing wave equals to y1 plus y2. Mathematically, by using these two, by having these two equations, we just total up these two equations, giving you 2a cos kx sine omega t, using trigonometry. Alright, so this is the main equation of standing wave, where listen carefully, 2a cos kx now representing the amplitude of the standing wave. This is the amplitude of the standing wave lah. Okay, and then 2a represent 2a cos kx representing the amplitude of particle x. What do I mean? For x equals to 1, this is the amplitude. X equals to 2, this is the amplitude. X equals to 3, this is the amplitude. See, the amplitude of each particle are different. It depends on its position, which is x, isn't it? So 2a cos kx now representing the amplitude of particle x. Okay, while 2a representing the amplitude of the standing wave. Okay, so correction 2a cos kx representing the amplitude of particle x. So at different position or at different x, the amplitude also different. Alright, so we can see here lah. And then 2a now representing the amplitude of the standing wave. Alright. Okay. So what is A? A is the amplitude of our progressive wave. This is A. Right? A. Amplitude of the progressive wave. So after the superposition, what happened? The amplitude now become double, which is equals to 2A. Alright. And for this part, don't forget, okay, you need to know what is the difference between the progressive wave and the standing wave. I think there are 4 different points to be discussed. Okay, you need to know this because in exam they may ask you to differentiate, okay, the progressive wave and the standing wave. Next part is the intensity. The intensity symbol is I. So what is intensity? Intensity is the ratio between power and area. So this A representing area. Power is the rate of energy. So intensity is the rate of energy per unit area. And remember, the sound wave just propagate in all direction. So seems like the area should be in spherical area or surface. So for any spherical shape or area, the area is 4 pi r squared. So r representing the distance between the source and the point, okay, or the surface. So the unit of intensity is watt per meter squared according to this equation. Okay, and remember 2 factors, okay, affected the intensity. The first one is the amplitude squared. Okay, the second one is r squared, where amplitude squared and I intensity, they are directly proportional, while I and r squared, they are inversely proportional. Okay, it means that when the amplitude of the wave is increased, so that I also increase. And then for the distance, when the distance just increase, the intensity should be decreased, okay, because they are inversely proportional. Alright. Then, what is the application of the standing wave? For this chapter, we are discussing about 2 things, which is the stretched string, and we are discussing about the musical instrument. Okay, seems like a guitar, violin, also the air column. So for the air column, it just separated into 2, which is for an open pipe, also for a closed pipe. Okay, so there are so many examples. Still the same. Maybe we are talking about the trumpet, about the recorder, something like that. Alright, so let's start by the stretched string. Okay, there is a string fixed at 2 ends. Alright, so for the first mode, okay, or the first frequency, how do we get the equation? Alright, so what do we have now? 2 notes and 1 anti-note, isn't it? Alright, so in this case, remember this is 1 lambda. So L here representing half lambda, isn't it? Just a part of this. Alright, so L equals to half lambda. So lambda equals to 2L. According to the equation of V equal to F lambda, F equal to V over lambda. And by rearrange this equation, you will get this. So this is the first part. So we are discussing about the first frequency. So F1 equal to V over lambda, where lambda equals to 2L. So that you will get F1 equals to V over 2L. Okay, for the second part, which is on the second frequency, how to get the equation? Okay, so there are 2 antinodes. Okay, so this L now equals to 1 complete lambda, isn't it? So L equals to lambda. According to the equation of V equal to F lambda again, so F equal to V over lambda, and here lambda equals to L. So F2 equals to V over L, where V over L still equals to 2V over 2L. Okay, I need to expand this equation because I want to get this V over 2L, where V over 2L now equals to F1. So giving you equals to 2F1. Okay, alright. So what is V here? This is the speed of the wave, okay, which is on the string. So how do we get this V? Using the equation of V equals to square root of T over mu. What is that? T is the tension and mu is mass per unit length. So mu equals to m over L. Okay. Alright, for the third part, we are discussing about the third frequency or F3, how to get the equation. So there are three antinodes. Okay. So how many lambda do we have? Half lambda, another half, giving you 1.5 lambda or 3 over 2 lambda. So here L equals to 3 over 2 lambda. So that lambda equals to 2 over 3 L. Okay, we just rearrange the equation. You will get this. Again, F equal to V over lambda. So we are discussing about F3 equals to V over lambda, which is 2 over 3 L. By rearrange the equations, you will get 3V over 2L equals to F3. So again, V over 2L now giving you F1, isn't it? So equals to 3 F1. So according to this situation, F here should be Fn. So Fn equals to V over lambda n. So according to this, it seems like our n equals to 1, 2, 3 and others. Okay, it just equals to the round number here. So based on that, okay, we may simplify that for any stretched string, our n just equals to 1, 2, 3, 4, 5 until nth, okay, where n1 represented the first harmonic, okay, n2 represented the second harmonic, n3 representing the third harmonic, okay, where first harmonic now is our fundamental mode, nada asas, okay, and then second harmonic now representing our first overtone, nada lampau pertama, okay, and the third harmonic now representing our second overtone, okay. So 1, 2, 3. Remember that is for the stretched string. Okay, let's start by the air column, which is under closed pipe. Okay, for the closed pipe, what happened now? The antinode just formed at the open end. At the closed end, it just under knot. Okay, so according to the situation, okay, L equals to how many lambda? Let's discuss about F1. This is quarter lambda, isn't it? Okay, because according to this, okay, this is one complete lambda. The pattern just now, just until this, isn't it? So this is quarter lambda, which is lambda over 4. So for the first part, in closed pipe, this one is quarter lambda. So L equals to lambda over 4 or lambda equals to 4L. Again, F equals to V over lambda. So F1 equals to V over 4L. So this is the basic equation of closed pipe lah, for the fundamental mode. And then for the second part, okay, how many lambda do we have? Quarter, quarter, and quarter. So 3/4 lambda, isn't it? So L equals to 3/4 lambda, or lambda equals to 4 over 3L. So based on F equal to V over lambda, so equals to V over 4 over 3L. By rearrange these equations, you will get F equal to 3V over 4L, where V over 4L equals to F1, isn't it? So that F equals to 3F1. So by having this, this is our N actually. So Fn equals to F3 lah, because Fn equals to NF1. So N now equals to 3, so this is F3. Alright. Okay, next. For the third part, how many lambda do we have? Quarter, 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 and quarter. So how many segment do we have? First segment, second segment, third segment, fourth segment, and fifth segment. Okay, so L equals to 5 over 4 lambda. Because we have quarter plus quarter plus quarter plus quarter plus quarter, giving you 5 over 4 lambda. So by rearrange the equations, you will get lambda equals to 4 over 5L. Substitute into the equation of F equal to V over lambda again. You will get V over 4 over 5L. Alright. So by rearrange the equations, giving you 5V over 4L. Again, V over 4L now representing F1, isn't it? So it just equals to 5F1. So again, this is our N. So Fn equals to NF1. So F5 equals to 5F1. Okay, seems like for this case, our N start by 1 and then followed by 3, 5, 7, 9, 11. Okay, we are talking about the odd numbers, isn't it? So for this, for any closed pipe, Okay, our N is 1, 3, 5, where N1 is the first harmonic, okay, which is our fundamental mode or nada asas. And then N3 is our third harmonic, which is the first overtone. And then N5 is our fifth harmonic, which is our second overtone. Okay, you need to know this because in exam, they may ask you, okay, just in terms of overtone or harmonic. So we need to know what is our N now. By giving you harmonic, we just take the numbers directly. For example, what is the speed of 11 harmonic? So our N equals to 11. But let's say by asking you about using overtone terms, what is the speed of the third overtone? Okay, third overtone N equals to, see, 7 lah. Because 1, 3, 5, 7, isn't it? So fundamental mode, first overtone, second overtone, third overtone. So third overtone is N equals to 7. See, we need to know this. Alright. Okay. Next, let's turn to the next part, which is under open pipe. Okay, what is the difference between open and closed pipe? Okay, open pipe, both ends just open. What does it mean? At both ends, we have the anti-knot. Okay. Alright, so this is the first pattern of open pipe. Okay, how many lambda do we have? Half lambda, isn't it? Okay, so here this is half lambda. So according to this case, L equals to lambda over 2. So that lambda equals to 2L. So from the equation of F equals to V over lambda, lambda equals to 2L. So that F equal to V over 2L. So this is F1, our fundamental mode. Okay. Remember, there must be an anti-knot at both ends. So half lambda for the first one. For the second one, okay, how many lambda do we have? This is one complete lambda, isn't it? Crash to crescent. Okay, so L equals to lambda. So based on the equation of F equal to V over lambda, so giving you F equal to V over L. So V over L still equals to 2V over 2L. Alright, I need to expand the equation because I want to find this term, V over 2L. So V over L equals to 2V over 2L, where V over 2L giving you F1. So equals to 2F1. That one is F2 lah. Okay, and for the third part, how many lambda do we have? Okay, 1 lambda and half lambda. So 1 and half lambda. So L equals to 3 over 2 lambda, giving you lambda equals to 2 over 3 L. Substitute into the equation F equal to V over lambda. So giving you V over 2 over 3 V over 2 over 3L. So by rearrange the equation, giving you 3V over 2L. Again, V over 2L giving you F1. So equals to 3F1. Okay, that one is F3 lah. Seems like same as our stretched string before, isn't it? Where our F start by 1, followed by 2, and followed by 3, isn't it? Okay, so in this case, still the same as the stretched string. So N equals to 1, 2, 3, 4, 5, and others lah. Alright, so N1 is the first harmonic, N2 equals to the second harmonic, N3 equal to the third harmonic. The first harmonic is our fundamental mode, followed by the first overtone, second overtone, third overtone, fourth overtone, something like that. Okay, so again, by using terms or harmonic terms in the question, we just take the numbers. And for example, what is the frequency of the fifth harmonic? So our N equals to 5 lah, fifth harmonic. Or by giving you overtone terms in the question, what is the frequency of the fourth overtone? Fourth overtone of the wave. Okay, kalau for fourth overtone, okay, fundamental, first, second, third, fourth. Fourth N equals to 5 lah. And because 1, 2, 3, 4, and 5. So we need to know what is the difference between harmonic and overtone. So again, by giving you harmonic terms, we just take the numbers directly. For overtone, we need to plus by 1. Okay, because we just start by the fundamental mode. Okay, lastly, we are discussing about the Doppler effect. Okay, what is Doppler effect actually? Doppler effect actually, we are discussing about changes in frequency received by the observer by having motion, okay, either by the source or by the observer. All right. For example, for this case, this is the source. Let's say this is the speaker. Now the speaker now is moving to the right, moving towards O, moving away from P. Okay. So moving towards, what happened? The lambda becomes shorter. And moving away, what happened? The lambda become longer, isn't it? So in this case, when the lambda becomes shorter, the frequency is higher lah. And because the wave is quite closer to each other, kan? Closer to each other means that the number of wave reach the observer now is more. Okay, all right. Compared to this, and when lambda becomes longer, the frequency are lower or smaller here. All right. Okay, so we just assume that frequency as the sound lah. When the source moving towards the observer, the sound getting by the observer is louder, isn't it? Then the frequency is higher. Or when the source is moving away from the observer, what happened? Okay, the lambda is longer or the frequency is smaller or lower, means that the sound also become weaker. Okay, this is the way, simple way to understand the concept lah. Alright, so in this case, according to Mr. Doppler, the idea is now giving you an equation which is F, this is Fk, Fk is the apparent frequency. Suppose Fa, Fk just in Malay actually, which is F ketara. Okay, that one is apparent K, apparent frequency. So apparent frequency equal to V plus minus Vo over V minus plus Vs, suppose, they are inverse, multiplied by F, this is the frequency of the source. Okay, so what is Vo or O observer, S is source. It's quite easy for you to remember. OPQRS, O come first, so we just put O at the upper side, followed by S. Okay, again, OPQRS, O come first, so we just put O at the upper side. At the bottom here, just S lah. Alright, so okay, Vs is the velocity of the source, Vo is the velocity of the observer, Fk is the apparent frequency getting by the observer, and F is the frequency of the source. Alright, so this is the tip lah. Okay, when the observer approach the source, V0 is positive. When the observer move away from the source, V0 is negative. When the source move away from the source, Vs is positive. When the source approach the observer, Vs is negative. Okay, for any static observer or source, Vo or Vs just equals to 0, means that they doesn't move. Okay, what does it mean by this? It's quite simple. I don't like to memorize this, but I like to understand the concept. Okay, it's quite simple. Alright, so let's start by this case. The source approaches stationary observer. So this is the observer and this is the source. So the sound just comes from the source. Now the source is moving towards the observer. Okay, what happens when the source just come towards the observer? The sound become louder, isn't it? Okay, now the question is V plus minus V0 over V minus plus Vs times by the frequency of the source. So in this case, the observer just keeps static, isn't it? So V0 equals to 0. Cancel out V0. What do we have? Just Vs only. So is it plus or minus? Okay, please refer to this question. The source comes towards, means that the sound is louder, isn't it? Become louder. So seems like F here should be greater. To have greater frequency here, the values at the bottom part here should be smaller, because something divided by smaller values giving you greater values, isn't it? So it just be minus. This is the way. Okay, or the source is moving away, moving away from the observer here. So seems like the sound getting by the observer is weaker lah, because the source moving away. So F is smaller. To get smaller F here, the values at the bottom here should be larger, isn't it? Because something divided by larger value giving you smaller F here. So to make it larger, it just plus. This is the way. Okay, or maybe for this case. Alright, now the source is static. but the observer is moving now. Okay, the first one is moving towards. Okay, before that, what do we have? Just VO. So the source is static here, so no Vs. Vs just cancel and to be 0. So the question is V plus minus V naught over V only. Okay, now moving towards. What happened to the sound getting by the observer? Should be louder, isn't it? Means that F is higher. So to get higher F, the values at the top here should be greater lah, which is plus, because greater values divide by something giving you greater F here. So plus. Or when the observer just moving away means that the sound getting by the observer is weaker. So weaker means that F here should be smaller. To get smaller F, the values at the top here should be smaller. So it must be minus. So this is one way how do we know the speed note just in plus or minus. Actually, there are so many different methods can be used. Okay, but I like to make a story, a simple story like this, so that I can see the equation clearly for any case given. Okay, I think that's all for chapter 10. Okay, so after this, you may try to answer the tutorial question and we just continue by the tutorial later. Okay, that's all. Thank you. Assalamualaikum.